Let's jump right into this explainer and uncover how scientists solve microscopic mysteries that are literally hiding in plain sight. Our modern world is just packed with complex mixtures. We're talking everything from the medicine in your bathroom cabinet to the food sitting on your plate. But how do we actually know what's really inside them? How do we prove a product is safe or, say, catch a clever counterfeit? Well, that's exactly what we're unpacking today. Now, headlines like this one about quinoline yellow or E104 spark immediate panic, and understandably so. If a food coloring is suspected of causing things like hyperactivity, asthma, and rashes in kids, parents naturally want it gone, right? But before governments can just ban a product or pull thousands of items off supermarket shelves, how do regulatory bodies actually prove that a specific, totally invisible chemical is hiding in our food? I mean, you can't just stare at a yellow drink and spot the E104 molecules with your naked eye. It's the exact same question we might ask about something as simple as a pen. Is that black ink really just black, or is it a hidden mixture of chemical secrets? To figure this out, we can't just guess. We've got to think like forensic scientists and build our very own chemical analysis toolkit to literally pull matter apart and expose its true identity. Moving into Section 1, the mystery of mixtures. Before we start cracking chemical cases, we really have to establish the ground rules of matter. We toss the word pure around a lot in everyday language, right? We buy pure orange juice and don't even think twice. But to a chemist, orange juice is absolutely not pure. In chemistry, a pure substance must contain only one specific type of element or compound, period. And a great physical test for this is temperature. A pure substance will have a very sharp, exact melting point. Mixtures, on the flip side, are two or more substances that aren't chemically joined together, so they end up melting over a kind of blurry range of different temperatures. This particle model brilliantly illustrates a pure substance. If we zoom all the way down to the molecular level, like this model of pure water, notice how every single molecule is completely identical. You've got one oxygen atom bonded to two hydrogen atoms over and over again. There are absolutely no intruders here. But here, we have a mixture. This is way more like that cup of coffee you probably had this morning, or a complex formulation like a medicinal tablet or a cleaning product. You've got completely different substances sharing the exact same space, but crucially, they are not chemically bonded to one another. They're just mingling. Formulations like this are actually incredibly important. They're carefully measured mixtures designed to produce a useful product with very specific, reliable characteristics. All right, on to Section 2, the magic of chromatography. So, here's the million-dollar question. When we encounter a complex mixture, how do we pull it apart to see the individual pure substances hiding inside without accidentally triggering a chemical reaction that destroys all our evidence? Enter paper chromatography. This is the ultimate detective's tool. It's a strictly physical separation technique used to separate mixtures of soluble substances. Because it's purely physical, no new chemical substances are made, and the original chemicals aren't altered at all. It relies entirely on solubility to pull the hidden components of a mixture apart so we can actually see them. The secret behind chromatography is basically a microscopic race between two phases. First up, we have the stationary phase. That's the absorbent chromatography paper. It just sits there, it doesn't move. Then we have the mobile phase, which is the solvent liquid, like water or ethanol. As this liquid travels up the paper through capillary action, it sweeps the mixture along for the ride. The different dissolved substances in our mixture have different affinities for the paper versus the solvent. So highly soluble substances are deeply attracted to the mobile phase, meaning they get carried much further and way faster up the paper. Let's look at Section 3, setting up the experiment. Now, the physical setup of this investigation needs to be incredibly precise. You can't just toss some ink and paper into a bucket of water and hope for the best. Let's walk through the actual procedure to see how this builds into a lab test we can run on plant dyes, food colorings, or those mysterious inks. First, you draw a pencil start line near the bottom of the chromatography paper. Then, carefully place small, spaced-out dots of your suspect mixtures right on that line. Lower the paper into a container with just a small amount of solvent, and then you just let physics do the work. You wait for the solvent to travel up the paper before taking it out to dry. Okay, let's play a quick game of spot the mistake. Looking at these two setups, the one on the left is absolutely perfect. Notice how the solvent level is well below the pencil line. But on the right, oh boy, a student made some fatal errors here. First off, they drew their start line with an ink pen instead of a pencil. Why is that a disaster?
because that ink is going to dissolve in the solvent and run right up the paper, totally contaminating the entire test. And if that wasn't bad enough, the water level in the beaker is way too high. It's actually submerging the ink spots. So instead of traveling up the paper, our chemical suspects are just going to wash away into the water bath. Case closed, and definitely not in a good way.
But hey, when done correctly, we get this beautiful result called a chromatogram. Let's bring back our suspect from earlier, the quinoline yellow E104 additive. Here, we run a pure sample of E104 on one side and the extracted food coloring next to it. Remember our rule, pure substances leave just one single spot, while mixtures separate into multiple spots. As you can see, the food extraction separated into 3 distinct spots, which proves it's a mixture. But here is the crucial part. None of those 3 spots perfectly align horizontally with the pure E104 spot. Because of that, we can definitively say, no way, this food does not contain the banned additive.
Which brings us to Section 4, Cracking the Code with Math.
Look, seeing colorful spots line up on paper is fantastic for a quick qualitative check. But in a court of law or a high-stakes pharmaceutical lab, scientists need hard, quantitative evidence to make a definitive match. This is where we calculate the RF value, which stands for retention factor. Because different compounds have exact, highly predictable retention factors in specific solvents, we can use these mathematical ratios like unique fingerprints. By calculating the RF value of an unknown spot, we can cross-reference it against a huge database of known values to positively identify our suspect.
And honestly, the math behind this is surprisingly simple, but incredibly powerful. The RF value is just the distance traveled by the substance divided by the distance traveled by the solvent. Both of those distances are measured right from that baseline pencil mark we drew at the very beginning. And since we're dividing a distance by a distance, the RF value is just a ratio. It has no units whatsoever, and it's always going to be a number between 0 and 1.
Let's actually crack a real practical case together. Imagine a student is investigating a mysterious new pain-killing tablet. They run the chromatographer and take their measurements. The center of the unknown substance's spot traveled exactly 20 millimeters up from the baseline. Meanwhile, the solvent front, which is the maximum height the liquid reached, traveled 50 millimeters. So, does this mysterious tablet contain paracetamol, aspirin, or ibuprofen? Well, let's plug our numbers into the formula. 20 millimeters divided by 50 millimeters gives us an RF value of exactly 0.4. When we pull up the lab's reference table, paracetamol is 0.33, aspirin is 0.37, and ibuprofen is 0.40. Boom, it's a perfect match. We just positively identified the active ingredient in our medicine using nothing but a piece of paper, some solvent, and a little bit of math. How cool is that?
Next up, Section 5, the Expanded Toolkit.
Now, paper chromatography is absolutely amazing for soluble inks and dyes, for sure. But scientists actually have an entire arsenal of specialized equipment for interrogating other types of tricky matter. I mean, what if our suspect is an invisible gas or maybe a dissolved metal? For volatile mixtures and gases, we upgrade to gas chromatography. The core principles are the exact same, but the phases change. The mobile phase is now an unreactive carrier gas, something like nitrogen, that sweeps the sample through a column. The stationary phase is a thick liquid coated on the inside of that column. And instead of getting spots on a piece of paper, this machine plots peaks on a computer graph. The number of peaks reveals exactly how many different compounds are in the mixture, the position of the peak tells us the retention time, and the sheer height of that peak, that exposes the exact quantity of the substance. It's literally incredibly precise. But what if we're tracking metal ions dissolved in a solution? Well, we can bring the heat. By dipping a wire loop into our sample and holding it directly in a roaring blue Bunsen burner flame, the thermal energy actually excites the electrons in the metal. And when those electrons fall back down to their normal energy levels, they release light. It's beautiful to watch. Lithium glows the striking crimson, sodium burns a brilliant yellow, and potassium shines a bright lilac. It's a super rapid, highly visual way to identify metals. Sometimes, though, those flame tests get clouded if you've got a mixture of metals. When that happens, we have to force those dissolved invisible ions to reveal themselves chemically. By adding sodium hydroxide to our sample, we trigger a precipitation reaction. Suddenly, out of nowhere, those dissolved ions form bright, solid, insoluble precipitates. Copper-2 forms a vivid blue solid, iron-2 turns into a sludgy green, and iron-3 drops out as this dramatic brown rust. It's literally like forcing a chemical suspect to step out of the shadows and show their true colors. So,
From catching illegal food additives in our everyday soft drinks, to identifying the life-saving active ingredients in essential medicines, all the way to tracking complex environmental pollutants in our water systems, these analytical tools are truly the unseen guardians of our modern world. They take the invisible and they make it visible.
So I'll leave you with this question. If you had the power to break down any everyday product and expose exactly what's hiding inside it, down to the molecular level, what would you analyze first? Let that linger in your mind for a bit. The next time you drink a vibrant soft drink or pop a painkiller for a headache, remember the brilliant chemical detectives and the incredible scientific toolkit working tirelessly behind the scenes to make sure it's exactly what it claims to be. Thanks for joining me on this explainer, and keep questioning the world around you.